Dear students, hello. In the previous class, we discussed about circuit simplification and why it is needed. We also discussed various forms like SOP and POS and how do they help in circuit simplification. Today, we are going to learn another important topic called registers. Also, we will discuss memory and its related concepts. So, let us start with registers. A register is a memory location within the CPU itself, designed to be quickly accessed for purposes of fast data retrieval. Processors normally contain a register array, which houses many such registers. The registers contain instructions, data and other values that may need to be quickly accessed during the execution of a program. Registers are normally measured by the number of bits they can hold. For example, an 8-bit register or a 32-bit register. Registers are now usually implemented as a register file, but they have also been implemented using individual flip-flops, high-speed core memory, thin film memory and other ways in various machines. There are different types of registers. Let us discuss them one by one. First one is program counter. This register is used to hold the memory address of the next instruction that has to execute in a program. This is to ensure that CPU knows at all times where it has reached, and based on that it is able to resume following an execution of an instruction that it has executed correctly. Then comes instruction register IR. This register is used to hold the current instruction in the processor while it is being decoded and executed, in order for the time of the whole execution process is to be reduced. This is because the time needed to access the instruction register is much less than continual checking of the memory location itself. Next is accumulator A. The accumulator is used to hold the temporary results of operations performed by the arithmetic and logic unit. Then comes memory address register MAR. This register is used for storage of memory addresses, usually the addresses involved in the instructions held in the instruction register. The control unit checks this register when needing to know which memory addresses to check or obtain data from. We have another register called memory buffer register MBR. When an instruction or data is obtained from the memory or elsewhere, it is first placed in this memory buffer register. The next action to take is then determined and carried out, and the data is moved on to the desired location from this register. Next is flag register. The flag register is specially designed to contain all the appropriate 1-bit status flags which are changed as a result of operations involving the arithmetic and logic unit. Apart from these registers, we have other general purpose registers. These registers have no specific purpose, but are generally used for the quick storage of pieces of data that are required later in the program execution. These registers, like accumulator, hold intermediate results or data values. Typically, there are several dozen of these registers in a CPU. Look at the figure to see how a register looks like. So, this was some brief discussion about registers. The next topic which we are going to discuss in due course of time is memory hierarchy. But before we take up the concept of memory hierarchy, let us first of all review some basics. Let us begin with a clock cycle. A clock cycle is the period of the waveform that the clock generates. That is, The length of a clock cycle is the amount of time from the start of a high value to the start of the next high value. So, it is measured in time units. The frequency is the inverse of the period. It is the number of cycles per unit of time. Frequency is usually measured in hertz. 1 hertz, abbreviated as Hz, equals 1 cycle per second. For example, 100 hertz means 100 cycles per second. When it comes to frequencies, the prefixes kilo, mega, giga and so on are powers of 10, not 2. So, 1 megahertz is 1 million hertz or 10 lakh cycles per second. The length of a clock cycle whose frequency is 10 megahertz is 1 by 10 raised to power 7. It is equal to 10 raised to power minus 7 seconds. Look at the figure. It illustrates the clock cycle. In the figure, you can see the rising and falling edge. The length between two rising edges is a clock cycle. In actuality, the switch between high and low states does not take 0 time. There is a small amount of time needed to make these transitions, as shown in the next figure, which is a more accurate depiction of a clock signal's waveform. Clocks are used to synchronize changes of state in sequential logic circuits. A sequential logic circuit, as we have already discussed in the previous lecture, is a combinational circuit with one or more elements that retain the state, for example, flip-flops. The state of a sequential logic circuit can be changed either when the clock line is in a high state or when the clock line changes state. If the state changes when the clock line changes state, it is called an edge triggered circuit. If it changes when the clock line is in a high state, it is called a level triggered circuit. I hope registers and clocks are clear to you. Now we will discuss about various memory units. The memory unit is the part of the computer that holds data and instructions for processing. Although it is closely associated with the CPU, in fact it is separate from it. Memory associated with the CPU is also called main memory, primary memory or internal storage. Let us discuss various memory units beginning with RAM, also called random access memory. It is a main memory and is used for the execution of the programs. Any program that needs to be executed is brought to this memory where its execution takes place. It is a volatile memory, which means that its contents are lost as soon as the computer system is powered off. Look at the figure, it shows a RAM. There are two basic types of RAM in common use today: static and dynamic random access memory, abbreviated as SRAM and DRAM respectively. Both are physically organized as an array of memory cells. Both use a decoder whose input is a set of address lines to select one or more memory cells for the memory operation. Both can store data as long as power is applied. However, even when powered, a DRAM loses data if it is not periodically refreshed, whereas in SRAM the data can be stored without any kind of extra processing or refreshing. As a result, SRAMs are less complex than DRAMs. The performance of a memory is measured in two ways: by its access time and cycle time. The access time is the time required to select a word and read it. The cycle time is the time required to complete a write operation. Next is ROM, also called read only memory. It is a special type of memory which can only be read and contents of which are not lost even when the computer is switched off. It typically contains manufacturer's instructions. Among other things, ROM also stores an initial program called the bootstrap loader, whose function is to start the computer software operating once the power is turned on. Read-only memories can be manufacturer programmed or user programmed. While the manufacturer programmed ROMs have data burnt into the circuitry, user programmed ROMs can have the user load and then store read-only programs. PROM or programmable ROM is the name given to such ROMs. Information once stored on the ROM or PROM cannot be altered. However, another type of memory called EEPROM allows the user to erase the information stored on the chip and reprogram it with new information. Examples are EEPROM and UVEPROM. So, we can say that RAM is a volatile memory, whereas ROM is a permanent memory having a limited storage capacity. We have another type of memory called secondary or auxiliary memory. It includes devices that are peripheral and are connected and controlled by the computer to enable permanent storage of the programs and data. Magnetic medium was found to be fairly inexpensive and long lasting medium, and therefore became the preferred choice for auxiliary storage. Floppy disks and hard disks fall under this category. The newer forms of storage devices are optical storage devices like CDs, DVDs, pen drives, zip drives, etc. Look at the figure. It shows various secondary storage devices. Now, let us study about memory hierarchy. To this point in our study of systems, we have relied on a simple model of a computer system as a CPU that executes instructions and a memory system that holds instructions and data for the CPU. In our simple model, the memory system is a linear array of bytes and the CPU can access each memory location in a constant amount of time. While this is an effective model as far as it goes, it does not reflect the way that modern systems really work. In practice, a memory system is a hierarchy of storage devices with different capacities, cost and access times. CPU registers hold the most frequently used data. Small, fast cache memories nearby the CPU act as a staging area for a subset of data and the instructions stored in the relatively slow main memory. The main memory stages data stored on large slow disks, which in turn often serve as staging areas for the data stored on the disks or tapes of other machines connected by networks. Memory hierarchies work because well written programs tend to access the storage at any particular level more frequently than they access the storage at the next lower level. So, the storage at the next level can be slower and thus larger and cheaper per bit. The overall effect is a large pool of memory that costs as much as the cheap storage near the bottom of the hierarchy, but that serves data to programs at the rate of the fast storage near the top of the hierarchy. It is important to understand the memory hierarchy because it has a big impact on the performance of the applications. If the data your program needs are stored in a CPU register, then they can be accessed in 0 cycles during the execution of the instruction. If stored in a cache, 1 to 30 cycles, if stored in a main memory, 50 to 200 cycles, and if stored in disk, tens of millions of cycles. Here then is a fundamental and enduring idea in computer systems. If you understand how the system moves data up and down the memory hierarchy, then you can write your application programs so that the data items are stored higher in the hierarchy, where the CPU can access them more quickly. This idea centers around a fundamental property of computer programs known as locality. Programs with good locality tend to access the same set of data items over and over again or they tend to access sets of nearby data items. Programs with good locality tend to access more data items from the upper levels of the memory hierarchy than the programs with poor locality and thus run faster. For example, the running times of different matrix multiplication kernels that perform the same number of arithmetic operations but have different degrees of locality can vary by a factor of 20. Look at the picture. Here in this picture, we can easily notice that whenever CPU wants to access data, it first of all accesses it from the registers. If the data is not available in registers, then that data is accessed from the cache memory, and if again the data is not present in the cache memory, then the data is accessed from other memories which are away from the CPU, thus resulting in more delay in accessing the data. Here in the figure, it is shown that if data is present in the registers, then accessing it merely takes 300 picoseconds. Otherwise, the time for accessing the data goes on increasing from 1 nanosecond to 20 nanoseconds or millisecond and so on. Now, what should be the objectives of a memory hierarchy? First one, to minimize execution time of executing programs. Second one is to maximize the throughput of the computer. And the third point is to minimize response time, subject to the constraint that high speed memory is limited in size, and this can only happen if data becomes available to the CPU as fast as it can. So, we can derive a result from this statement that in order to achieve the set objectives, frequently required data should be stored in the memories which are very near to the CPU. Now, when we talk about memory hierarchy, we need to remember some points. Those are, regardless of how many levels are in the hierarchy, data copied between adjacent levels of the hierarchy only. We focus on just 2 levels at a time. Also, a block is the smallest unit of information that can be present in a 2-level hierarchy. In other words, regardless of which 2 levels are the subject, the smallest transferable unit of the 2 levels is called a block. Another point to remember is that a hit occurs when data requested by the processor is present in the upper level of this 2 hierarchy. Otherwise, it is a miss. The frequently used term in memory hierarchy is the hit ratio, which is nothing but the fraction of memory accesses resulting in a hit. Hit time is the time to access the upper level, including the time to decide if the access is a hit or a miss. The miss penalty is the time required to replace a block in the upper level with a corresponding block in the lower level, plus the time to deliver this block to the processor. Remember, performance is affected by 3 factors: the hit ratio, the time that it takes to access the upper level, and the miss penalty. The miss penalty dominates these times. A trade-off to keep in mind is that as the size of the upper level increases, although the hit ratio increases, the hit time also increases. Before moving on to how data moves between different hierarchy levels, let us first look at a TLB. Without any other hardware to support it, a virtual memory system will slow down execution by a factor of 2, because every memory access will require 2 accesses, one to retrieve the page table entry and one to do the actual load or store operation. This is too inefficient. A TLB called translation look aside buffer is a special cache for the page translations. The TLB caches the most recently used portions of the page table. When a cache and TLB are both present, the question is, should the TLB or the cache be accessed first? If the cache is physically indexed and physically tagged, it means that the cache is referenced using physical addresses, not virtual addresses. This means that the virtual addresses must be translated before the cache is accessed. In this case, the TLB access precedes the cache access. The alternative is to access the cache with virtual addresses. in which case it is called a virtuality addressed cache. In this case, the TLB is not accessed first. The processor sends the virtual address directly to the cache. The data is the actual data stored at that virtual address. On a cache hit, the data in that virtual address can be delivered to the processor, but on a cache miss, the virtual memory system must be used to locate the physical page in which the memory address resides. Look at the figure. It shows the complete operation about how data is accessed by the CPU. The figure shows that when the processor references a page and if that page is present in the TLB, the physical page number is copied from the TLB into the physical address register and the control bits are updated as necessary. Otherwise, the page table base register contents are accessed and used with the page number to locate the page table entry in physical memory. Then memory is accessed and the page table entry is read into the MMU, that is memory management unit. If the page is in memory, then an entry is added to the TLB for this logical or physical page pair, replacing an existing entry if necessary, otherwise it means a page fault has occurred because the page is not in the memory. When this happens, the hardware circuits in the MMU generate an exception to the CPU to indicate the fault. The exception causes the running process to be preempted and its current program counter to be saved, usually into an exception PC register. The operating system finds the page on the disk and chooses a frame into which to place it. If it is, the operating system finds the page on disk and chooses a frame into which to place it. If it must, it replaces an existing page, writing it to the disk first. The operating system updates the page table to contain the correct translation, setting the valid bit, and the entry is copied into the TLB. The reference to the page is re-executed. This is how data is accessed in a hierarchical way. So, this was an example showing memory hierarchy and how different memories are accessed. So, with this we complete our lecture. Hope you have understood it. Finally, concluding our lecture, let us summarize what we have learned today. We discussed what are registers and why do we need them. We studied various memory units like RAM, ROM, PROM, EPROM, etc. besides some auxiliary memories, and at last we studied memory hierarchy and how data is accessed from various memory levels. I hope that these topics are now clear to you. In the next lecture, we will study about number systems. Thank you. Have a nice day.